Okay, good morning again. Today we are going to study MTI and Doppler radars, pulse Doppler radars. First, we'll be introducing Doppler effect. What Doppler effect is will be the first that we'll be discussing. And then we'll be talking about continuous wave Doppler radar and its pulse version. And then we next look at MTI and go into the details of MTI, its operation, clutter effect, and filter design. Okay, we have studied so far radar range detection, range estimation. Now we are talking about speed, how to detect a target in motion, and how to extract that target speed when there is a clutter, there are objects around the target which are fixed or slowly moving. And we then look at Doppler effect in order to extract the motion of the target. From the physics, maybe the first year or the high school, we may know this effect, Doppler effect. If we talk about a signal, we talk about amplitude, frequency, and phase. These are very basic parameters of a signal, a radar signal, typically. We talk about amplitude, frequency, and phase. And electromagnetic waves, when they travel in space, their phase progress with the distance through this formula. So for every lambda in space, phase add 2 pi, okay, adds 2 pi. So if we take L as lambda, 1 lambda, then the phase is going to be 2 pi. When we take L, 2 lambda, so electromagnetic wave travels 1 more lambda, and then the phase will be 4 pi. So it progresses linearly with the distance. Now, let's think about the radar system shown in here. We have a distance of r from the radar to the target, and the target now is in motion. It has a speed of v, and there is an angle between the line from the target to the radar and the direction of the motion of the target, which is theta. Then we talk about radial speed, which is the speed of the target times the cosine of this angle. Okay, now let's think about this distance and look at how phase varies with the distance. As we consider radar pulse in here, we have two-way transmission, so round trip, which means that we got 2r distance. And then if we insert this 2r into here and determine the phase, it's going to be 2 pi times 2r over lambda, or 4 pi r over lambda. So for any time instant where the distance is r, the phase is going to be 4 pi r divided by lambda. Now, considering that the target is in motion, it has a speed of v, then we expect variation of the distance. So this r here is time varying function. So r of t simply. Then if we look at the phase will be time varying too. Then that's going to be phi of t simply 2 pi 2 r of t divided by lambda. Now, we know that from signals again, the frequency is proportional to the time derivative of phase. Okay, so if we take the time derivative of both sides in here, so the time varying r of t, its derivative with respect to t will give us the time derivative of the phase. Then we determine frequency. So we write this in here, and we see that the radial frequency omega d is going to be 4 pi over lambda VR, where VR is VR, yeah, that's right. And if we write this ft as 2 VR over lambda, then the radial frequency will be dependent on the phase variation. So the phase variation will be dependent on the distance variation. Distance variation with the time, as we said earlier, is about the motion of the target. And then we can extract the speed information of the target. Here, ft is defined as Doppler frequency. And when we transmit a signal at ft, frequency ft, the echo signal will be a shifted version of this transmitting frequency by the Doppler frequency. So ft plus fd. And it's, as you may see here, since the radial speed is dependent on the angle here, which is very critical, then the Doppler shift might be varying between varying in proportional with minus v and v, as cosine would take the values of -1 to 1. Okay. Now, in the next slide, we see how this radial speed varies with the angle. Here we have a radar, and we have several targets having different directions of motion. And as you can see, when the target here is moving away, so receding, then the radial speed is going to be simply from v cosine theta, where theta is going to be what? 180 degrees. So it's going to be -1. -1 times v is -v. So as the radial speed is -v here, then we expect that the Doppler shift will be negative, which means that the received signal frequency will be reduced by the amount of the Doppler shift. On the other hand, for a target coming into the radar, the radial speed is going to be, again, from the formula, v, since the angle is going to be 0. So the Doppler shift here is positive, which means that the received signal frequency will be increased simply by the amount of Doppler shift. Now, when the angle here is 90 degrees, okay, here is the direction of motion, here is the line to the radar, and the angle here is 90 degrees. Then, since cosine 90 degrees is 0, then the radial speed is going to be 0, which means that the Doppler shift is 0, simply. So then we can conclude that if there is a target moving in perpendicular to the direction of the radar, will simply induce 0 Doppler shift, which means that we cannot measure the motion there at this specific angle. We could not measure the speed, so we have to use something else if you want to know the speed of a target who is moving in perpendicular to the direction of the radar. Typically, we in practice we usually have an angle between 0 to 180 degrees, and very occasionally we might have such 90 degrees angle. So we usually take VR as V times cosine theta, and in most of the systems, we simply align or position the radar such that this angle becomes as minimum as possible, so that we can see the target on the line of the line from the radar to the target. So try to make this angle 0. Okay, what is frequency shift, or how phase as can be illustrated, their phase variation can be illustrated with time. Here we see a sinusoid. This is a very basic concept, but better to remember this as we'll be discussing in next slides. MTI processing, where coherence processing, coherence will be very critical. Here we have 2 sinusoidal signals, as you can see. Okay, the black and blue one, and the phase of the black sinusoid is fixed. It does not vary. As you can see, the frequency of the black one is not changing with time or distance. On the other hand, the blue one has a phase variation, and when they start from 0, they have started initially at the same phase, while after about 0.4 unit, we see a difference here, right? Where one makes the black one makes a dip, while the blue one makes a peak. Okay, so one is simply 180 degrees, while the other one is minus 180 degrees. So why? Because the blue one has a progressive phase variation. Okay. So we then, if we have constant phase at a receiver, or stable phase, stable frequency that we can generate a receiver, we can have a coherent system. So, which means that the phases are quite aligned and there is no ambiguity. Okay, let's see how Doppler frequency varies with radial velocity. Here you can see on the graph here, we have radial velocity in knots. Here we have frequency, Doppler frequency in hertz. It's a logarithmic scale, as you can see, and we have frequencies in here. the operational bands, which are typical in radar systems. Remember that 1 knot is 0.5 meter per second, which is about 1.8 kilometer per hour. And remember this formula. We simply here, the textbook simply transform this equation into a graph where you can easily see how Doppler frequency varies with radial velocity for different operational bands. Let's see, for example, about a velocity of 10 knots. Okay, and see how much Doppler shift we expect at different operational bands. Let's say UHF band, which is 435 megahertz, which is typical band for very long distance surveillance radars. We have about 20 hertz, right? 20 hertz Doppler shift. Okay. While for L-band radar, we have so 20, 30, 40, about 50 hertz. While for a W-band radar, which is 94 gigahertz, we have about 1,000 to 3,000, 4,000. So 4 kilohertz. Okay, you see how it varies, starting from several tens of hertz, goes up to several thousand hertz by only changing the operational band. Okay. Here we see an example. This is the case where the target is incoming. So the radial speed is simply V, as the cosine is 0. But the platform on which the radar is installed is also moving. Okay? So they're approaching to each other, which makes the speed is simply sum of the speeds of the platforms. So then the Doppler shift here should be calculated by considering the speed of the target as well as the speed of the platform. Okay, we have to add them up and determine the radial or relative speed, and then use it in calculating Doppler shift. Okay. Okay. Now we have 3 domains. Then we talk about carrier frequency. See, so the operational band that we are talking about. If there is a Doppler shift, and we expect received signal at f0 plus ft. So this is the received signal frequency. When there is an incoming target, so where the speed of the radial speed of the target is simply the speed of the target. And here the radial speed of the target is simply minus v. Okay, this is again the received signal frequency. Now we can subtract the transmitted signal. This is the transmitted signal frequency, and we subtract it from the received signal frequency. We get the Doppler shift domain, where we expect a Doppler frequency at ft, where we do not have the transmitted signal frequency anymore, right? Or minus ft. This is the Doppler domain. okay, after extracting the transmitting signal frequency. And then here we got speed domain, where we simply change here. Okay, so 2VR over lambda. So I just write FR here, lambda FD over 2 to get the speed domain where we got VR or minus VR. So these transformations from the received signal spectrum to Doppler spectrum and then speed domain, of course, require some processing at the receiver side. And in next slides, we'll be discussing how to process these signals. Before that, let's see MTI and pulse Doppler radar and also continuous wave radar. As we said earlier, MTI stands for moving target indication radar. We got pulse Doppler radar as another version of moving target or moving target detection or estimation. So we simply have MTI and pulse Doppler radar. They both use Doppler shift, but their processing and parametric variations could be possible. And we can see in here, as you see, we tune parameters differently in MTI operation and pulse Doppler operation. For MTI, PRF is very low, while for pulse Doppler, PRF is very high. Which means that in MTI, we got high PRI. In pulse Doppler, we have low PRI. Then in MTI, we have no range ambiguity, okay, as the PRI is high enough. While on pulse Doppler radar, we got range ambiguity as the PRI is low. On the other hand, we got Doppler ambiguity and MTI. We have no Doppler ambiguity in pulse Doppler radar. Okay, let's again go back to the first lesson and remember PRI concept. Okay, this was a typical illustration that we have been using for radar pulse train. Here is the duration of the pulse. We got a pulse repetition interval, PRI. And PRI was proportional to 1 over PRF. So we got symbols for that, TP. So TP is 1 over FP, as you might remember. Now for then MTI, we have low PRF, high PRI, and for pulse Doppler, we have high PRF, low PRI. So in next, we'll be discussing the advantages of each in detail and compare them. There may be a compromising solution where we can choose a medium PRF. So it's not high enough, but not low enough to say pulse Doppler or MTI. Then this could of course, present both range and Doppler ambiguity. So if we are able to tolerate some Doppler and range ambiguity, then we can use medium PRF. There is also a continuous wave Doppler radar where we measure only speed, not range, as we use only sinusoid. Usually it's used for detection of moving targets in clutter, only speed of the moving targets in clutter. Okay, what's clutter? Let's talk about this clutter concept. In most of the applications, we have many objects over the link or around the link and around the target that we want to detect. So all such objects over the link or around the target are simply called clutter. Sometimes clutter is considered at the radar receiver design as part of noise, let's say. Sometimes it's not. There may not be a common convention on that. But when we say clutter, simply, it should be something, an object that we do not want to receive echo signals, okay? So it could be anything. Let's say in this classroom, I just want to detect a student who is moving, let's say, and we have, as you see, chairs in here, and ball, sailing, ground, and we expect echo signals coming from all those objects while we are trying to detect the moving targets or moving student. So all of the objects around this target are simply clutter. Okay? Now, it's a very then important concept to extract the motion in here, considering all such clutters. Okay? As you might remember, we simply measure range to the target when you use a pulse type radar. We can now measure the motion. We can detect motion. And if we have a good antenna system, we can measure angular position. And as you might remember from the missile range profile, we can classify some of the targets and identify them, discriminate different targets. So we have lots of information actually we can collect by using a radar about the target. Now, in pulse Doppler radars, we have analysis techniques, and as you might remember from signals and systems, we as electrical engineers mostly prefer to work in either frequency domain or time domain. So in MTI and pulse Doppler radar concepts, at the receiver side especially, we'll be dealing with filtering techniques, and they may be studied in either frequency domain or time domain. So let's again go back to the signals and systems and remember the general concept. If we have a system, let's say an impulse response of h of t, okay? If we got an x input, x of t, the output simply x of t convolution h of t. This was the basic system concept we studied in different courses. Now we can use this time domain model, or we can use frequency domain version where we got h of f, the transfer function of the system, and the input signal spectrum and output signal spectrum. Now, this is going to be multiplication. Okay, so convolution in frequency domain is equivalent to multiplication in frequency domain. Sorry, convolution in time domain is equivalent to multiplication in frequency domain, vice versa. For any non-deterministic, so a random signal, we again use h of f. But here, instead of x of f, since we do not know the spectrum of the signal, that's a random process. Instead, we use power spectral density. Okay, and the output signal's power spectral density will be the input signal's power spectral density times the magnitude squared of the transfer function of the system. So this is for deterministic signals, this is for random signals, and this is for time domain signal analysis. So we'll be using somehow these concepts in next slides. Okay, this is a table, two tables actually, showing requirements and typical parameter range of pulse Doppler and MTI radars. It was taken from Radar Handbook by Skolnick again, third edition. And here in table 4.1, you can see some pulse Doppler applications and requirements. Here we see radar application, and on the right-hand side, we see requirements. You see, starting from surveillance, spaceborne surveillance goes up to missile warning, where we have short detection range, very low false alarm rate, while for surveillance, we have long detection range with accurate range data. So it's widely, you see, varies depending on the requirement. We change the parameters. In table 4.3, we have X-band airborne fire control radar. It's PRF and duty cycle. You can see for medium PRF, high PRF, and high medium PRF and high PRF, which means that here we talk about both pulse Doppler radar and MTI radar. They are basically the same. They use Doppler effect, both, but the processings are different and parameters are different then. The most significant parameter here is PRF, of course. One is low. It's low. In other one, it's very high. So in here, then, you see for high PRF case, we talk about several hundred kilohertz PRF, where the duty cycle goes up to 50%. Remember the duty cycle, it was pulse duration divided by pulse repetition interval. Okay, so this means that if I use high PRF, we actually transmit half of the time and then listen the other half of the time. Okay, here we see a simple continuous wave Doppler radar. This uses Doppler effect again. It's a very simple block diagram. Of course, in practice, this is quite complicated. Just to give the idea here, we have an oscillator where we generate a sinusoid. Typically, we can write this just like cosine 2 pi ft. Okay. This is transmitted through an antenna. There are typically two antennas here. I just show one as I take this picture from the textbook. but in practice, there are two separate antennas, one for transmit, one for receive. So I know the transmitting signal frequency, and if there is a motion in the target, then we expect Doppler shift. And then the received signal frequency will be simply shifted by FD. So we can write that just like, for example, K times A. This K is a constant showing the attenuation or other effects in the channel. Cosine 2 pi, so FT plus minus FD. T. Okay, so this is a signal that we can get from the receiver, and there's going to be a leakage from the transmitter, very weak signal coming from the oscillators, so the transmitting section to the receiver. So we can take this receiver, for example, and here is transmitter. Now we got a detector. The detector is typically a mixer. Now in the laboratory of the course, you may remember mixer, right? Up conversion, down conversion. We have already studied that. Let's see here. Here is a mixer. We got a signal coming from the target. Let's say cosine 2 pi ft plus fd t. And we got a signal coming from the transmitter side, which is cosine 2 pi ft t. So mixer simply generates all the variations of these two frequencies, okay? As you might remember from the laboratory, if this is frequency A, if this is frequency B, let's say, the frequency of the output signal is going to be n times Fa plus minus m times Fb. Okay? All the multiples of these frequencies appear at the output of the mixer, and we usually use a filter, a low-pass filter. So we connect a low-pass filter here. To eliminate high frequency components, as we are interested in Doppler frequency only, which is very small compared with the transmit signal. So if we tune the band of the low-pass filter, so the cutoff frequency of the low-pass filter, we can easily see only the Doppler frequency within this low-pass filter, at the output of the low-pass filter. Okay, so we simply here get the difference, let's say Fa minus Fb, which gives us what? Ft, right? The Doppler frequency. So here, the detector is simply a mixer along with a low-pass filter. And then we can use a digital processing, for example, to identify the exact value of the Doppler shift, as we might have more than one frequency, not only the Doppler shift of the target, but also some, shifts, Doppler shifts due to the clutter. So we have to use a signal processing there to extract the Doppler shift. Next, let's see pulse Doppler radar. This is a little bit complicated, as you can see in here. We simply here then transmit a sinusoid and then off, and then another sinusoid and then off. So this is a typical radar waveform that we have been using from very beginning. we got a pulse duration here, and then pulse repetition interval, PRI, or TP is 1 over FPE. There may be two antennas again in here, or we may use just one antenna. If we use a duplexer, we can use single antenna. And a duplexer is a device which pass through signal from 1 to 2, while the signal from 2 to 3. So no transmission from 1 to 3, okay? There's an isolation from port 1 to port 3. And when we look at the receiver, as we may expect, there should be something at the receiver which extracts the Doppler shift, okay? Now, in pulse Doppler radar, we may use a Doppler filter bank at the output of the mixer and low pass filter again, and we can estimate precisely the Doppler shift. Okay, we can have a break in here. Okay, let's continue. In this slide, we are deriving the form of received signal for the illustration of the radar system that we have been using frequently. We got a transmitted signal, AT sine 2 pi ft, a sinusoidal at frequency FT. It travels by R, hits on the subject, object, target, and then echo signal return to the radar. Here the target has a speed of V, and its radial speed is V times cosine theta, where theta is the angle between the line of sight from the radar to the target and the direction of the motion of the target. When we look at the round trip time, it's going to be 2R divided by C as electromagnetic waves travel at the speed of light, And when we look at the echo signal, then we may think about the time varying distance from a fixed distance R0 minus VR times T. Okay, so the distance between the radar and the target is simply decaying. It decreases with time, and it's dependent on the radial speed of the target. So if we look at the echo signal right here and insert this and this into this equation, we got the received signal, a sinusoidal signal with amplitude AR and a constant phase due to the initial position of the target R0 at R0. We see that the received signal changes with a factor of 2 VR over lambda. We have already described that in the previous slides. And remember that at the receiver side, we got a mixer again, where we have the received signal, that's X R of T, and X transmitted signal, xt of T, and the output is going to be multiplication of two signals as we have shown in the previous slide. That's going to be multiplication of two sines or cosines, and it gives you the difference frequencies. And we use a low pass filter at the output of this mixer, and take the frequencies within the low pass band. Usually these are the frequencies at the Doppler shift or around the Doppler shift. So we see the different signals in this form. This is the constant term again at the initial position. And the different signal, as you can see, is a sinusoidal with frequency ft, the Doppler shift. So if the Doppler shift is zero, then the different signal will become zero, which means that there is no phase variation, so there is no frequency variation, then there is no object, there is no target. Okay, so how about the radar pulse width and the Doppler shift relationship? If you have a long pulse and a large Doppler shift, then we can easily measure the speed of the target within one pulse only. But this is not common. Mostly we have to collect Doppler shift over many pulses. Here we see how this could happen when there is a Doppler shift, as I said previously. Let's say FT, the Doppler shift, which may have a Doppler period, let's say FD. So you see Doppler shift is just a sinusoid simply. Let's say this is a sinusoid with duration TD, then the Doppler shift is going to be 1 over TD, right? So we can take a Doppler shift duration over time, and then if this is smaller than the pulse duration, so if TD is less than or equal to tau, then I can measure Doppler shift using single pulse. So this shows that case. You see the Doppler shift here, TD, you see, is much smaller than tau. Or simply 1 over FD is much smaller than tau. Or inversely, we can say FD is much greater than 1 over tau. Okay? So what happens if the Doppler shift is proportional to the pulse width? Then we can see the second slide where the Doppler shift again is high enough, but it's comparable with the inverse of the pulse width. And there may be somehow ambiguity in this case. One pulse may not be enough to measure the Doppler shift. Finally, which is very common in surveillance type radars, here the Doppler shift, as you can see, okay, has so the TD is much greater than the pulse width. So we have to take several pulses, collect the phases, and then combine the phases to measure the Doppler shift. Okay, this is typical for aircraft surveillance radars. So simply, there is a relationship between the Doppler shift that we expect and the pulse width. We have to know how many pulses we need to process to extract the Doppler shift, depending on the pulse width and the expected or estimated Doppler shift. Okay, one of the subjects that we deal with in MTI processing is delay line canceller. Here there is an illustration. Suppose that we, okay, let's see, we have pulse sequence again. Okay, so this is one. Here is the TP. Okay, now I got a phase in here, let's say phase 1, and the next, let's draw the next pulse. Another TP. So in delay line canceller, we simply get the phase of the pulse and wait the next pulse and look at the phase of the next pulse and then get the difference. Okay, if there is a stationary target, we expect that the phase does not change, right? Okay, if there is no change in phase, then there is no moving target. Okay, so in this illustration here, as you see, here, let's say the first pulse response, and here is the second pulse response. I mean, when I say pulse response, actually we talk about one TP, one PRI. Okay, we transmit one pulse and listen the echo signals, and then transmit the second pulse, listen to echo signals, and then subtract them. Okay, but phase, not amplitude. So then if there is an object, as you can see in here, for example, here we got, as you see, a variation here, but that's constant. It does not vary with the within the successive pulses. So this means that there is no motion here. There may be some clutter in here, but there is no motion. Here, for example, the signal here, when we compare them in the second pulse, second TP, we see that the signal varies slowly. The amplitude goes down, and here also the signal increases slowly a little bit compared with the previous one. So when we get the difference, okay, this one and this one, we get the echo signal where we have a motion. Okay, so there it means that there is a target in motion at that distance. Okay, here how to process MTI signals. Remember that MTI is a low PRF system, so high PRS system. There is no range ambiguity in MTI. And we use delay line canceller, as we have illustrated in previous slide, and we'll be giving the details of this DLC concept in next slides. And here we see how we process the received signal. We got, so you can imagine that here we got again LNA, remember the radar concept, and then mixer, and then low pass filter, okay, a chain where we get the baseband signal, and then we use an analog to digital converter here, and then use a delay line canceller. We get the, let's say, pulse 1 and pulse 2. So 1 TP duration. There's a 1 TP duration delay. So we get the difference, and then we get the absolute value, and then use a digital to analog converter if there is a display, analog display, to show the variation. If there is a motion, then we will see objects, we'll see targets at that locations. Here is the detailed block diagram of MTI system. The one of the critical concept in MTI is phase coherency, as we said earlier. Whatever we generate, a sinusoid, let's say, in the receiver or transmitter, we have to know exactly how its phase is changing in the system. If there is a phase change, we have to know that. There should be no ambiguity on phase change. So whenever we generate a sinusoid, it should be reliable in phase. It should be coherent. We have to know the phase value. There should be no drift. There should be no phase change in the system. Otherwise, we may measure the Doppler shift incorrectly, because Doppler shift is, remember the first slide, is dependent on the phase variation. So whenever there is a phase variation, we expect Doppler shift. So if there's a phase variation due to the system, then that's going to be an error in Doppler shift. Okay, this is why we call coherent system, very well designed system for such phase ambiguities. For this purpose, there are two different synthesizers, so two different generators in here. One is a stable oscillator, and there is a coherent oscillator in here. And this stable oscillator is used to the received signal, received mixer, the first mixer in here. And the coherent or reference generator is very critical. It has a very good stability in phase. That's why we call coherent oscillator. And it is the initial signal that's produced by this coherent oscillator, and then mixed with by using to the frequency that we want to use anyway. And then with a power amplifier, it's transmitted. So we are now sure that the transmitted signal is coherent enough. And then this is also used by stable oscillators as a reference signal at the receiver chain. So if we try to look at the receiver and transmitter in here, here is the receiver with the antenna, of course, together here. And here is the, this part is the transmitter. We can simply split that into two. So that's the reference signal, which is common to both sides, very critical. So what happens in here? We generate a local oscillator frequency, let's say FL, that's mixed with a, sorry, this is not correct. This should be the other way. So that's mixed with the carrier frequency FC. Okay, so this is FC. So it's transmitted through the power amplifier and duplexer. So the transmitted signal frequency is FL plus FC. Okay. Next, we get the echo signal. There we expect some Doppler shift. So the echo signal will be FL plus FC plus minus FD. And that's mixed by FC. So we remove FC simply. Then this should be FL, by the way. Sorry. FL plus minus FD, which is which is very low frequency signal. Typically, it's filtered. Here we typically have match filter actually. And then we use a phase detector to extract the phase information, and then use a delay line canceller. So before the delay line canceller, we simply extract the phase variation, okay? Phase variation. So this is going to be the input to the, remember the previous slide, where we have a delay line canceller and then rest of the processing. Here, this is a little bit complicated block diagram. That's a pulse Doppler radar. The previous block diagrams simply present a general idea of the MTI operation. Now here we have a detailed pulse Doppler block diagram. This is taken from, again, radar handbook. This is not, this cannot be found in the textbook, by the way. As you can see, it's a quite complicated system. We got an antenna system here, which is typically electronic. It has an electronic scanning where there are transmit-receive modules. And there is going to be a beam steering, of course. And we can see the transmitter chain in here and then receiver chain where there are actually 4 different channels. And we know most of the components now, LNA, mixer, and some additional processes for noise and clutter, and then match filters. As you can see, there are 2 mixers in here. It's very much like the previous slide where we got a coherent, right? Coherent oscillator in previous slide. Now we got the same actually, and there's a stable local oscillator in here. So that's an extended version of the previous slide actually. It includes all the channels, full high-level design we see in here. And on the bottom, we see the signal processing part where we use typically FFT. So we simply analyze the phase varying signals in frequency domain. Okay, you can see the details of this system from the radar handbook by Skolnick. Okay, we now look at delay line canceller in time domain and then frequency domain. As you might remember, this was one portion of the MTI receiver. At the output of the phase detector, we got a delay line canceller. Remember that the delay line canceller is simply look at the, let us draw it. We got a pulse sequence again. So what I do here, so I take the signal, this part, the echo from this, let's say this is the echo from this part, and then the echo for the next pulse until here, right? So another echo coming from this second PRI, okay? Now measure the phase variation over this signal, not amplitude, phase variation. And then, as we have shown previously, heterodyning process, mixer, low pass filter, at the output of the low pass filter, we subtract 2 signals and then get the different signal. So this slide shows how to get the time domain filtering, so delay line canceller over these two signals. We have already given some illustration about that. First, for the first pulse, first TP, we got simply k times sine 2 pi ft t minus phi, which is offset introduced by the first position of the target. And ft is the Doppler frequency. We assume that we have a Doppler frequency here. Next, for the second sweep, so this is the first, so this one, and this is the second, so this one. There's going to be a delay of TP with the same Doppler shift. Now we get the difference using the, remember, the subtraction, simply this involves two voltage signal and get the difference. This is not mixing, be careful. This is simply sine A minus sine B. So V1 minus V2. When we look at the difference, we see that we can write that in this, using this identity, we can write that as two terms. The first is a sine, the second one is a cosine. Now, as you can see, this is the signal that we already received. So this is not about the difference. This is about the transmitted signal, just 2 pi ft. And there is another component here, which shows us the response of the DLC, the result of the operation. Okay, so this is then, this can be written as the transfer function of the DLC, delay line canceller. This is 2 times sine pi ft tp. Now, when we plot this transfer function, at the bottom you can see that it has zeros. The first zero occurs when ft becomes 0, because sine 0 is 0. Next, whenever the Doppler shift is equal to 1 over fp, so we can write this fd times 1 over fp. Whenever the Doppler shift is equal to the pulse repetition frequency, the response becomes 0. So we got 0 right here, here, and here. So all the multiple values of the fp, we got 0 response, which means that if there is an object, there is a target whose Doppler shift is equal to the PRF or multiple of PRF, our system gives 0 response, which means that I couldn't detect those targets. This is very critical. Okay, so whenever the target has a Doppler shift equivalent to the multiple of PRF, we got 0 response. We couldn't detect those targets. It was a time domain analysis. How about the frequency domain analysis? Let's build up a system for DLC, delay line canceller. As you might remember, we got an x of t. So x of t, again, let us write that. Here is the pulse. So here is the first TP, and then second TP. Okay, so this is going to be this one, for example, and this is going to be this delayed version, for example. So get the difference. If we enter a direct delta, okay, then we can measure the impulse response of the system. From the systems, signals and systems, you might remember, we got a system, we apply direct delta at the input, and the output becomes h of t, right? Because the impulse response is simply the response of a system against direct delta. Okay, so if we apply direct delta to this system, so imagine that this is the system for which we would like to determine impulse response, and this is going to be direct delta, right? This is going to be direct delta here, direct delta minus TP. Okay, so the result here is going to be direct delta minus direct delta T minus TP. Okay, which is going to be the impulse response of the system. So this is time domain signal. Now we can take Fourier transformation of this and see that the transfer function becomes this. Okay, we know this from Fourier transform. Okay, we simply look at the Fourier transform table and then or the textbook, we can easily write this. We can multiply this by exponential terms and put that in this form. Okay, the amplitude spectrum, the transfer function, the magnitude of the transfer function again becomes 2 times sine pi ft tp, just like the previous slide where we use time domain derivation. Okay, we were talking about that h of f. Remember, it was 2 sine pi ft tp. Okay, or 2 sine pi ft divided by fp. Okay, so as we said earlier, whenever the Doppler shift here becomes the multiple of fp, then the transfer function here becomes 0, which means that the delay line canceller creates 0 response, and this is equivalent to the case where there is no moving object. But actually we have. Okay, we have. Why? Because the Doppler shift is equivalent to PRF. PRF is a non-zero parameter, which means that there is a motion, there is a target, a moving target, but the frequency, Doppler shift of the target is equivalent to PRF. So this is called blind speed actually. So at some specific values of the speed for some targets, the response of the filter becomes 0. And we couldn't detect those targets at that frequency, at that speed. Okay, that's why we call blind speed. Blind speed. Then this causes ambiguity in speed measurements. Okay, so what we'd like to do typically, we'd like to push this 0 response up. Okay, so this can only be possible by making PRF large enough. So if you increase PRF, then you can somehow reduce ambiguity in speed measurements. Okay, when we increase PRF, we can reduce the ambiguity in speed measurements. When we increase PRF, the TP, the PRI, decreases. When PRI decreases, we have range ambiguity. So then there's a problem here. There's a trade-off between range ambiguity, okay, range and speed ambiguity or Doppler ambiguity. If we try to reduce speed ambiguity, we have to increase PRF, which causes ambiguity in range. So we have to find a way to resolve this problem. We'll be discussing that in next lessons. Okay, how many blind speeds do we have? We simply extend this by considering the number of PRFs in here. If we take one PRF, that's going to be the first blind speed. If we take the Doppler shift as 2 times the PRF, that's going to be second blind speed, third blind speed, fourth blind speed. So it goes in that so on. Anyway, we choose the number of blind speeds in here. Okay, here we see a graph which is very important for understanding of range and speed ambiguity. Here is the unambiguous range. So this is a 3-parameter graph, by the way, be careful. And here is the PRF, which is 1 over PRI. And here is the first blind speed. So we are 1. And here's the formula. You might remember this. There are several operational bands in here. For example, this is 9 to 4 gigahertz. So this line represents 9 to 4 gigahertz. While this one here represents 220 megahertz. Okay. So let's see, where do we have ambiguity in speed and where do we have ambiguity in range? Okay. When we look at this, you can see we have unambiguous range in this region. Okay. Unambiguous range in this region, but ambiguity in range. Okay, here we got ambiguity in range. Why? Because you see the unambiguous range here, it goes down, and then we talk about several tens of nautical miles only. And here we have unambiguous range, and we got ambiguity in speed. Okay. So whenever the range is unambiguous, we have speed ambiguity. Whenever we have unambiguous speed, we have range ambiguity. We can then choose the parameters for this range, for example, where we have both range and speed ambiguity. If we can tolerate both, then we can choose the parameters, so the PRF here and unambiguous range in here, and then first blind here. So we talk about this region. That's going to be medium PRF systems, as we can expect. What else? How to reduce the blind speed? There are several more ways, and usually they are preferred. We can reduce the frequency, as you can see here. Here, when the frequency increases, the ambiguity, right, increases. We can see here actually the wavelength is proportional to the speed. Okay, if we reduce the frequency, the wavelength increases, so the first blind speed increases, then there is going to be no ambiguity. But when we reduce the operational frequency, we reduce the resolution. Okay, and usually we would like to increase resolution too for any radar systems, and so that's going to be a problem. We can use high PRF, that's another method. And this was the case, as I said earlier, there's going to be ambiguity in range. Or we can use multiple PRF, which could be a good solution, or multi-carrier system. These are also possible solutions for reducing blind speeds and ambiguity. Here we have a problem. Please try that, attempt to solve that at home, and then you can ask your questions in the next office hour we have. Okay. Now we will be dealing with delay line canceller now and clutter. Okay, remember the clutters again. In the classroom, we have given an example. I'd like to detect one student moving there, and there are too many objects in the classroom. This is very typical in military or civil systems, where there may be object that you want to detect, and there may be lots of things around that. And these objects are called clutters, and we'd like to ignore them and then extract the information about the target. Okay. And if there is a motion, then we expect some Doppler shift. So by using delay line canceller, we can measure the Doppler shift and then estimate the speed of the target, so the motion of the target, so the target. But usually there are some imperfections in the system which cause some Doppler shift too. Just like, for example, the phase coherency, if the system is not coherent enough, or if there is a motion, mechanical vibrations or something like that, there are always some imperfections, and then you may not get zero Doppler shift. You may have somehow a Doppler spectrum, actually, not a single value, but a spectrum. It's illustrated in this slide for idealized clutter. Let's say a vehicle moving on the mountain, and you got an airborne radar, and then you'd like to detect that vehicle. Okay, as the vehicle is moving on the ground, it's not easy to detect it by simply looking at the echo signal magnitude, because there are too many things around that. So you may look at the Doppler shift. You assume that the vehicle is moving, and all around, the clutters are stationary, so that you can extract the Doppler shift and detect the target. Ideally, that's the case, you imagine, but in practice, this is mostly impossible because of the imperfections of the system. You are an airborne platform, and there are imperfections there, as we said earlier, and also the clutters. The clutters may slowly moving. Let's say if there's a wind, the trees may be moving. Okay, so this idealized spectrum, clutter spectrum, is not, as we can understand from the name, not realistic. Instead, we have some realistic clutter spectrum at the bottom, as you can see. So there may be somehow, you see, especially in this area, we have some spreading, where we can measure some Doppler shift due to the clutter, or here. Okay, these are the regions where my DLC gives Doppler shift, but that's not due to the target, that's due to the clutter. Okay, so one way to model this clutter spectrum is to use this Gaussian spectrum. You can see on the right hand side W of f, which has a Gaussian form, as you can see. There is a constant term and then a frequency in here, and then sigma c, which is the standard deviation of the clutter, hertz, and also hertz per meter. We can convert this standard deviation into hertz per meter. So divide by lambda, that's a normalization. And then on the response, relative response of the delay line canceller, as you can see, the spectrum of the clutter is simply covers this area, and this area, as you can see. These are approximate drawings, of course not perfect. And you see two transfer functions in here. One is single cancellation, and the other one is double cancellation. So if I use 2 pulses or 3 pulses, I can use 3 pulses or 2 pulses. Single cancellation means I have 2 pulses, okay? Double cancellation means I have 3 pulses, 3 TP duration. So its response, as you can see, the transfer function follows sine squared. So very similar to first or single cancellation. It's square of that. It's smooth, as you can see. It's smooth, yeah. So we can somehow get rid of this clutter effects, right? We can reduce the effect of clutters by using double cancellation. We can increase the number of pulses. Instead of taking 3 pulses, you can take n pulses, which makes this response more sharper. So you can eliminate clutters around this 0 and NFP. Okay, this was the end of the presentation. There are problems from this Skolnick's book, problems 1, 3, 4, and 5. Please study the subject well and then attempt to solve those problems.